Okay, in this lecture, we'll take a look at two basic examples involving the potential energy stored in capacitors. So let's take a look immediately at the first example. It refers to the following circuit diagram. Let me go ahead and read it to you here, however. As always, please copy it into your notes. Okay, so for the following circuit element, this diagram here, find the voltage and charge across each capacitor given the following values of capacitance. C1 is 1 microfarad, C2 is 2 microfarads, C3 is 3 microfarads, and the battery here, which has a voltage V0, is 10 volts. Also find the potential energy stored in each capacitor. Usually with these types of problems, they're usually simple and straightforward, but you end up with essentially a bunch of little relationships with a lot of unknowns, which you then have to solve for. So let's immediately begin to break the problem down in the following manner. Okay, so first of all, here on the left-hand side of this portion of the diagram, we have here two capacitors that are in series with respect to each other. Recall that when capacitors are in series, they have the same charge. So then therefore, let's say that there's a Q1 associated with this capacitor, but it's the same as this capacitor here. In addition to that, because these two capacitors are in series with respect to each other, they have different voltages. So right here is going to be a voltage V1, right here is a voltage V2. Now the total voltage, V1 plus V2 like so, is the same as that of the battery V0. So right off the bat, by looking at those capacitors that are in series, I have this expression here. Okay, and then also with these capacitors in series, let's go ahead and write down relationships for the charge. Q1, which is the same here as it is here, because once again, these two capacitors are in series. So for C1, we can write the Q1 as C1 V1. And then for the capacitor here, we could write the same Q1 as C2 V2. So immediately by looking at the two capacitors here that are in series with respect to each other, now what I end up with here are two equations and two unknowns. Here is the first expression, and then the second expression now is to take these two values of Q1 and set them equal to each other. Like so. All right, so let's go ahead and do the math here and solve for V1 and V2. So to do so, I'll take this expression here and solve it for V1. So it's C2 over C1 times V2. And then we'll take that expression and plug it into here. Okay, so V1 is C2 over C1 times V2, and then plus V2 is equal to V0. And now let's just solve for V2. So factor out the V2 from each term here, like so. And then go ahead and divide. Like so. Okay, now taking a look at the ratio here down in the denominator of the expression, we have 2 divided by 1, so this is a total of 2, and then plus 1, which gives me 3. So V0 over 3, so 10 divided by 3 is 3.33 volts. Okay, so now that I have that value for V2, let's just go ahead and then say use this expression here to find the V1. Let's just go ahead and do it that way. So C2 over C1 times V2. So 2 over 1 times 3.33 is 6.66 volts. It's actually 6.67 volts. I've rounded off a little bit here. And the reason for that is because the total of 6.67 volts plus 3.33 volts, like so, equals then the total right here of 10 volts. So let's make sure that we take that into account right here in this calculation. Okay, now that I got all the voltages, then the next thing to find are the charges. So let's go ahead and jump up to the top board and find the Q1. Okay, I'm going to rewrite this value here for clarity as we go forwards. We're going to need it here as we continue. Same thing for V1. Let's get rid of this work here. Okay, now let's go ahead and find the Q1. Of course, we could use either of the two expressions. Let's just use this one here. So it's going to be 1 microfarad and then multiplied by right here 6.67 volts. This then gives us a value of Q1 that's 6.67 microcoulombs. It's okay to do a problem like this while keeping everything in terms of micro, which is the same thing as 10 to the minus 6. So once again, right here, the charge Q1 is going to be 1 microfarad multiplied by 6.67 volts. That's 6.67 microcoulombs. Q1, there we go, 6.67 microcoulombs. Okay, now let's jump to this capacitor right here. Let me move to the top board once again. Okay, this capacitor here is in parallel, if you will, with the battery. So then therefore the potential difference across the capacitor is the same as the potential difference across the battery. So this right here has a potential of V0. And then therefore I can now find a charge on this capacitor, we'll call it Q3, by just doing the following expression. Q3 is equal to C3 multiplied by that voltage of V0. So then therefore this is equal to 3 microfarads multiplied by 10 volts, which is 30 microcoulombs, like so. So once again, you end up with a bunch of little relationships here for a problem such as this with some unknowns, and then we solve for what we're looking for. Okay, now that I have the charges on each capacitor, the last thing to do is to find the potential energy stored. So let's go ahead and do that. Okay, so first of all, for capacitor C1 here, let's call the potential energy stored there U1. Okay, I'm going to go ahead and calculate U1 by doing the following. 1/2 C1 times V1 squared. This will then allow me to write my answer in terms of microjoules. So let me go ahead and do the math here on the calculator. We've got 1/2 times 1, 1/2, and then multiplied by V1 squared, so times 6.67 volts squared. So times 6.67 squared, and that then gives me a value of about 22.2 or so microjoules. Okay, do the same thing for capacitor 2. We'll call this U2, like so. So 1/2 C2 times V2 squared. So then therefore I have 1/2 times 2 microfarads, and then multiplied by 3.33 squared. And this comes out to be 11.09 or so microjoules. And then lastly, for capacitor C3, we'll have U3, 1/2 C3 times V0 squared. Remember, of course, that the voltage across capacitor number 3 is V0. So then therefore 1/2 times 3 microfarads times 10 squared, and this ends up being 150 microjoules. Okay, easy problem, just a bunch of little relationships and some unknowns. Okay, let's go ahead and move on to the next example in this video. In the next example in this video, I'm going to give you a deeper understanding at a more fundamental level as exactly where potential energy comes from. So we're going to see a little bit more fundamental physics in this example that follows. We'll take a look at a parallel plate capacitor to do so. Okay, let me move my file. Okay, let me do some erasing here. Okay, let's go ahead and take a look at the example. As always, copy it into your notes. Okay, a parallel plate capacitor of 1 microfarad. Okay, C equals 1 microfarad. That's 1 times 10 to the minus 6 farads. Okay, it's connected to a 9-volt battery. So V is 9 volts. Okay, the plate separation is 1 millimeter. That's small d. So 1 times 10 to the minus 3 meters. And then we just have the following. In part A of the problem, find the area of the plates. So the diagram associated with this, by the way, is just a diagram like so. Where here's our battery, and here's our capacitor of capacitance C. So in part A of the problem, in order to find the area A associated with the plates, right here, of course, is the plate separation D, then we use the expression for capacitance for a parallel plate capacitor. Recall that I've derived that expression for us previously. The capacitance for a parallel plate capacitor is epsilon naught A over D, where epsilon naught, the permittivity of free space, is this value here. Okay, so just solve for A, nothing more than that. So A is CD over epsilon naught. As long as everything is in the correct units, we'll end up with then a value of A in terms of meters squared. So I'm going to write the capacitance now as 1 times 10 to the minus 6 in my calculator. So 1 times 10 to the minus 6, then multiply by 1 times 10 to the minus 3 for D, and then divide by epsilon naught. So I do have to take care that everything is in their proper metric SI units when I make this calculation. And I end up then with A as being quite large, 113 meters squared, like so. Okay, I'm going to go ahead and double check that calculation just to make sure. Like so, and yeah, it ends up being 113 meters squared. Okay, part B, find the charge. Okay, so to find the charge now, I'll just do Q is equal to C times V. That's probably the easiest way to do that. So then therefore, this right here is 1 times 10 to the minus 6 farads multiplied by 9 volts. That's 9 times 10 to the minus 6 coulombs, or equivalently 9 microcoulombs, like so. Okay, part C, find the energy stored. So the energy stored, U, I'm just going to write as 1/2 CV squared. So then therefore, I have 1/2 multiplied by 1 times 10 to the minus 6, and then multiplied by V squared, so multiplied by 81, and that comes out to be about 4 times 10 to the minus 5, and this would be joules, like so. So once again, easy calculations here to make with the opening portion of this example. Okay, part D, find the electric field. So in order to find the electric field, we're going to use the kid's name to do so. Call that the voltage across the parallel plate capacitor is equal to the constant electric field multiplied then by the plate separation. So the electric field is going to be V over D. And incidentally, by the way, at this point you can go ahead and write the units of the electric field in this context as volts per meter. That's fine. Or you can keep it in terms of newtons per coulomb, either way. Okay, so 9 volts and then divided by 1 times 10 to the minus 3 meters. And this comes out to be 9,000. So 9,000 volts per meter, like so. Okay, and then in the last portion of the problem here, part E, this is where we start to get a little bit more fundamental. In part E of the problem, we're going to calculate what is referred to as the energy density. Here's what I mean by that. Let me write down some of these values here, however, that I'm going to need for this calculation. Like so. Okay, let me diagram out kind of like a blow-up picture, if you will, of our capacitor. So here's a close-up of the capacitor like so. So it has area A, plate separation D. Right here is the electric field E. Okay, here in this last portion of the problem, we're getting a little bit more fundamental, if you will, kind of getting a better understanding as to exactly where potential energy comes from. A vector field, such as an electric field, stores potential energy. We can calculate this in terms of what is referred to as energy density. Energy density is always referred to as small u. It's equal to energy per unit volume. So what I'm going to do is take the total energy that's stored in this capacitor U and divide it by the overall volume of the capacitor. When I do, I end up then with the units of this quantity as joules per meter cubed. As we'll see when I arrive at the answer, it's literally describing that potential energy is stored within a vector field, whether it be an electric field, such as what we're doing here in this calculation, or in a magnetic field, as we'll see later on in magnetism, or also in terms of a gravity field, if we were to go back and make that sort of a calculation. But now in this particular case, the energy density can be found in the following way. Okay, first of all, here in the numerator of the expression, I'm going to write this as 1/2 CV squared, where this right here is the voltage. And then we're going to divide by the volume of the capacitor. The volume of the capacitor is the area A multiplied by the plate separation D. Like so. Okay, now let me replace in the numerator of the expression, first of all, the capacitance with the following. Epsilon naught A over D. Then I'm also going to replace the voltage here with the kid's name, E times D. Like so. And then we'll divide by the overall volume of the capacitor, AD. And then when I do, notice that a bunch of things cancel out. So first of all, the area A cancels like so. Notice also that all of the D's cancel like so. And then therefore what you're left with for energy density is a fundamental expression. This expression here, it's literally describing that within a vector field, such as an electric field, there is a certain amount of potential energy that is present there in terms of joules per meter squared. So ultimately, potential energy is associated with vector fields, in this particular case, an electric field. Let's go ahead and get our answer here. That's why I kept this value here of the electric field from earlier. So I'm going to multiply that then by epsilon naught, of course. So 1/2 times 9,000, we'll square that, and then multiply by 8.85 times 10 to the minus 12. And when I do the math here, literally the energy density associated with this electric field is about 3.6 times 10 to the minus 4 joules per meter cubed. So it's in this context here, in terms of a charged up parallel plate capacitor, that you're starting to get a deeper understanding as to where potential energy comes from. Potential energy is literally stored within vector fields.